So this is the 7th lecture of CEE, and it is in this lecture we will start learning how to explore knowledge of the state in the state model to do feedback. And I would like to start by considering a very simple example. And instead of showing you the slides, let me use the whiteboard. So the whiteboard is this. Suppose that we have a system that can be modeled as a double integrator. So one example is the situation in which you have a current or a signal that controls the current, and you have a power amplifier, and you have a coil, okay? And this creates some magnetic field, and you have a small sphere. And you establish some referential, let's call it Y, and you want to model this situation. And the model is very simple because you have two integrators. You have two integrators. Let me call the position, so Y is equal to X1. So Y is equal to X1. That's the position. Now, the derivative of X1 is the velocity. So let's call it X2. This is the velocity, and this is an integrator. And assuming that the current is proportional to the force, then you have here your control variable, which is the current or the force, and you integrate it, and you get the velocity. So here you have the derivative of the velocity, which is the acceleration, is equal to the force. Okay, so if you apply Newton's law and assume that the mass is 1, then you get this system. Okay. Now, let's design a controller to keep Y at some desired position. So what do I do? I use a feedback controller from the output. So I have some reference, and I subtract it from the output. And I put here some gain, let's say K. Okay. Now, my question to you is this going to work? Of course, you can use the psychological argument. If the guy is asking us whether this works, it is because it does not work. Okay, but apart from that, because sometimes it can work. But what can you say about this control system? What do you expect that will happen to Y with this control system? you have some knowledge based on feedback, on root locus. What is the root locus here? You remember the diagram of the poles. So if this is a complex plane,
the system will be marginally stable.
That is to say, it starts oscillating. So
yes,
you will have something which will do like this without damping. So that's your theory. Time. Why?
Because it has two poles on the origin, and
so we have the open loop system has two poles at the origin. Good, two poles at the origin.
Yes.
That means a different color. Okay, and then what happens? When I do the feedback with this proportional gain, where do the poles go?
They go one up and the other down.
One up.
But they stay on the imaginary axis.
They stay on the imaginary axis. So you can even compute the poles. Okay, but so in this case, it does not work. Now, solutions for this, what can you do?
Add something inside of the feedback loop. Instead of being just a constant one, multiplying the signal at the exit, we put some variable depending on S on the feedback loop.
So instead of doing a proportional feedback, I do here, I place here something. What do you mean?
Adding a 0 in the left complex space, or 2.
I could not understand. You can say that in Portuguese?
Adicionar 0 no espaço complexo direito.
Okay, so I put a 0. How do I create a 0? So your suggestion is I create a 0 here. And how do I create a 0 here?
Multiply by S.
Multiply by S?
No, by to be in the left half plane, it needs to be S.
So I place it here.
Yes.
S
I'm not sure.
Something, some K1, let's say, some S plus alpha. How can I create this? Because this is a system with 1, 0 in no poles. So some approximation of this. Place another pole. Where shall I place the pole? To the right of the 0 or to the left of the 0?
To the left.
To the left, so that it is neglectable, no? And you end up, in this case, you will end up with something which is, let's use a different color, green. So the pole approaches this 0, and this 0 is dominant, so you will have something like this. Okay, because the center, the symptotic center, will be moved to the left. So this 0 attracts. Okay, so in this case, this will be S plus alpha, S plus beta. Okay, with beta bigger than alpha. Now, okay, this is one possibility. I could have placed this stuff there also. In terms of the root locus, it would be the same. Do you know what is the difference of placing this stuff here or there in series with K?
A função transferência malha aberta é diferente.
No, let's see what happens if you have this. Remember that what is, yes, it is, yes, it is different. That's right, that's the answer. But let's be more careful about writing this stuff here. So what is the transfer function between R and Y in this situation? So the closed loop transfer function is what? If you have A plus minus, and then you have B, what is the equivalent transfer function? Is
A over 1 plus AB.
A over plus 1 plus AB. That's right. So it's the direct function on the upper floor and the loop gain, 1 plus the loop gain in the lower floor. So here, what shall I get? What is the direct function?
K over S squared.
K over S squared. And here, 1 plus
1 plus S plus alpha over S plus beta times K over S squared.
which is what is written here, apart from the order, which is the same. Okay, so this is what? This is what you have K. You have K. And you have S squared plus K, S plus alpha, S plus beta. And this is K, S plus beta. And here you have S squared, S plus beta, plus K, S plus alpha. Okay? So be careful because you are creating here a 0. So this pole creates a 0 and it affects the, but for the purposes of the root locus is this one on alpha that is important. Now, any other option?
Can I ask a question?
Uh-huh.
Why did you put the S plus alpha on the closed loop part to create that 0?
You can do it, you can place it on the closed loop or in the open loop.
Okay.
As you see, if you place it in the closed loop, it will not be a 0 of the closed loop, you see? If you place it in the return function, the 0 will not be present in the closed loop function. This 0 in alpha is not a 0 of the closed loop, but it has the effect of attracting the branches of the root locus. If you have placed it there, then this alpha would be a 0. Okay, so you have the two options. You can have the two options.
But so on the root locus we draw it as if it was a 0?
So it works. You could have also done this. Okay. Then S plus alpha, S plus beta. Then S squared, 1 divided by S squared, and then this. This would also work, okay? At least in terms of, the root locus would be the same. But remember that the root locus gives you the closed loop poles, not the zeros. And the zeros in these two cases are different. So you can stabilize the system either by placing a 0 here or by placing a 0 here. Is that okay?
Okay, thank you.
Okay, and the difference is that in this case, this zero does not cancel that pole. Instead, in this case, this 0 will cancel that pole. So then you can discuss what is the best option for you. So we have already two solutions. Now, another solution to stabilize the system. No ideas? Oops. I'm writing too much. So S plus alpha. Okay. Another solution might be that, okay, I will clean this up. So I have my 1 over S here, 1 over S. And then I do a feedback of the output and also of the velocity, of the position and of the velocity. So I multiply this K1 and this by K2. I add. And okay, let's forget about that K. Let's leave that K out. Maybe we don't need it because we have already these two Ks. Actually, you don't need it. Okay, does it work? How can you see the transfer function in this case? You can rewrite this diagram in this way. So you replace the arrows. So you cut this wire from here and you connect it there. So what you get this output multiplied by K1. And then you have K2 multiplied by this point, multiplying this point. But K2 multiplying by this point, if you cut this wire and place it there to have an equivalent, you have to multiply by the inverse of this transfer function, which is S. So you must have K1 plus S K2. Let's put here the K. And now what happens? Do you agree that both these blue diagrams are equivalent?
Sorry, Professor.
Yes.
In this case, we don't have to add a pole on the feedback.
This is just for mathematical purposes. So if
okay,
you
so it's not real. It's just
yes. If you do it, if you implement it, you use this first the upper diagram. Okay, but if you want to compute the closed loop transfer function, you can do this trick. Of course, this is non-causal, but it's just for the sake of manipulating the blocks to compute the transfer function. So what is the transfer function here? How can you get the transfer function? the transfer function between R and Y is what?
It's K over S squared
K over S squared
over 1 plus K over S squared, K1 plus S, K2.
Am I right? Okay. So you can take here, multiply everything by S squared. And you get K S squared. And this is a K. Okay. So this is the transfer function. This is what is equivalent between R and Y. Now, what can you tell me about stability and possibilities to design to select the gains such that they are stable? What can you do? Or, for instance, comparing this system with the first system, the one with in red and green. So
by
yes?
changing the K1 and K2 values, we can either have purely we can eliminate, for example, the real part of the poles because they're going to be complex conjugates. We could.
I mean, you don't want to eliminate the real part. You want to actually create a real part so that you attract the poles to the left.
But yes, by changing K1 and K2, we can have the stability that we want.
Suppose that I say, I want poles in minus 3 and minus 5. Okay? How do I proceed? I want a characteristic polynomial, so a denominator, which is what? S plus. If I want to have
S
poles,
plus 3 and S plus 5.
S plus 3 and S plus 5.
We can calculate that, equal that to the denominator, and see what K1 and K2 is, assuming we already have K.
And we have a solution. So this is S squared plus 8S, isn't it? Plus 15. And here, what you have S squared plus K1 or K2, K S plus K1K. So suppose that you select K equal to 1. Select K equal to 1. It's a little bit chaotic, no? And K1 should be what?
15.
15. So compare, and K2?
8.
8. So in this case, you can place the poles anywhere. If I tell you, place the poles no matter where, you will always be able to find coefficients K1 and K2 such that you select these coefficients of this polynomial. Okay, so you can place the poles everywhere. Okay, so and here you don't have this problem of the pole here to make it causal, because this is something which is just for mathematical purposes. What you use is this. This is for implementation. Okay, this other is just a trick so that you can compute the transfer function, because it's not so easy to compute this transfer function. Okay, when you have multiple feedbacks, you don't have a simple rule. But by doing this trick of moving this branch to the output, Then you have a feed forward gain and a feedback gain, and you can apply the well-known for the computer transfer function. Is that okay? Any question about the details? No question. Okay. So what I want to say is, x1 and x2 form the state, position and velocity in this case. This is the second order system. So x1 and x2 form the state. And by feeding back the state, we could place the poles where we want it, at least in this case. Okay. Instead, if we have feedback from the output, then we have to use some tricks, like adding some zeros and poles. Okay, the poles are needed, so it's less flexible. Using the state, it's much more flexible. Okay, so the questions that we have here is this true? I mean, if I have a system of order n, by feeding back all the state variables, is it possible that I place the poles where I want? We are going to see that this is not so. But there are cases in which, yes, you can place them. In the issue is that the structure of the system must be such that it allows this problem to be solved. Okay? And we are going to study a concept called controllability. Controllability. I will show the slides in a moment. But let me write controllability. Controllability. And this concept of controllability will allow you to design in a simple way whether by feeding back all the state variables, you can place the poles where you want. So the objective of this example was first to show that by feeding back the state, you have more flexibility. And under some conditions, you can place the poles where you want by adjusting the feedback gains. You don't even need this pole, this gain here, this general gain here in series with the error. Any question? So let's look at the slides. So what are we going to study in this chapter? We start with this motivating example, and I will introduce these concepts of controllability and observability. And then we study the problem of linear state feedback for the regulation problem. The regulation problem is the problem in which you have a non-zero state and you want to drive it to zero. For instance, you have an airplane flying and there is some turbulence and you want to drive the position of the airplane to the steady state flight. You want to reject disturbances. That's a regulation problem. And we are going to learn how to do it with linear state feedback in a systematic way. Then, in many cases, you can't measure all the state directly to do the feedback. So we are going to learn how to develop what could be called a software sensor. So it's an algorithm that uses the model of the system and allows you to estimate the state based on observations of the input U and the output Y, and you estimate the state. And then we show a very useful theorem, which is the separation theorem, that says that you can design the feedback, the state feedback controller, and asymptotic observer for the state in a separate way. And when you put everything together, that is to say, instead of feeding back the state, you feed back the estimate of the state, then if you design them separately, then when you put everything together, it works. And the poles are the ones that you expect. And finally, we extend these results to situations in which you want to track not zero reference, but a non-zero reference. You want to drive your output to some point. Okay, so this is the contents of the second chapter of the course. Okay, so as for motivation, we have seen this example. I won't repeat it. No. Okay, let me again go to the whiteboard and to ask for your capabilities of invention. So let me clear everything. So we have our system that we know it's a double integrator. One over S and 1 over S. And we have y equals to x1. And then you have here the velocity that you don't measure directly. So you measure just a position, and you also have access to the value of u because you are imposing it. Okay, now we want to feedback the position and the velocity. The position we measure, but we don't measure the velocity. So we want to estimate the velocity. So how can I get an estimate of the velocity?
By deriving the output?
So one possibility might be you differentiate the output, and you get here some estimate. So I put a small hat. The hat is not so that it is defended from the sun, protected from the sun. It means it's an estimate of x2. Okay, so problems with the derivative.
It's not causal.
It's not causal. It's a non-causal function. And probably there is another situation. Suppose that you have suppose that you do observations. So you do a record. So this is time. And your y starts here and is at a constant rate, but it's not exactly at a constant rate because you have small reading errors. Your sensor has noise. Okay, so you would like to have a constant. If you had just this pure, okay, then the velocity would be what? If this is x1, then x2 hat would be what? Would be what type of line? The derivative of something of a straight line
Constant.
is a constant line, okay? But now you are differentiating, and suppose that you take the derivative here in this initial part. So it's probably here, but then you have something like this. So you have a much higher value, okay? And then it's this part here, and then so it's below, okay? It's probably even a negative value, can be a negative value. And then it's positive again. So it's there. So you start having something, okay. You see? So you are amplifying the noise. So the derivative has these two problems. It's non-causal. And if you have noise, even a small amount of noise, you are amplifying the noise to your estimate. You agree?
Yes.
Okay, so I can clean up this. My sketch was very bad, but you understood the point. So another option. So you want to compute x2. So you look from here. That's my eye. Okay? You look from here and you said, okay, I start from y and I look backwards. Where else could you look from?
In the input.
From the input. So let's look from the input. From here. So you pick up the u, and what do you use to estimate x2?
I also use the integrator.
Use an integrator. So if you have an integrator, then again, you have x2 hat 1 divided by s. Okay? And the integrator is much less sensitive to noise, so it's much better. So we clear our eyes, and we have this. Now, suppose that you have some disturbance, and the disturbances affect your system. So you have here some signal D. So that adds to you. You would have a problem because your x2 does not know anything about the disturbance. So this D would change a lot x2, but you are still estimating if there is no x2 because this is a kind of open loop system. So what could we use to modify the scheme? I'm not asking you to what is the modification, but what type of information can we use to modify the scheme? While you think, I'm going to redraw it in a better way. Disturbance. And So you do a replica of the first part. And you have here x2 hat. Okay, so what type of information can we use, can we explore to improve our estimate with respect to disturbances that act on the system, and of course to not act on your estimator, because your estimator in green, this is software, and in blue, this is physical. This is the physical plant in blue. So what could we do? Where can we pick? Yes?
Can we use the derivative and the estimator to compute the error? And then...
So use the output. Use the output. But it's not a derivative. What we do is we do a replica of our system. Okay? So another integrator. So this is a replica of our system. So here you have an estimate of x1, which is an estimate of the output. Okay? Now we have an error here. Plus, minus. If there are no disturbances and the initial conditions are the same, then our estimate of the output should be equal to that. Otherwise, we need a correction term. And the correction term is very simple. You just multiply this by gains, L1 and L2, and you add here. Okay? And now you have to design this L1 and L2, which I'm not going to do here. But now, at least it's clear that if your estimate is a bad one, you are comparing it with the output, so you understand your estimate is not good. And if L1 and L2 are convenient, later we are going to learn how to design L1 and L2 in a systematic way. If L1 and L2 are convenient, then what happens is that this error corrects the estimates. If the output is very close, if the estimated output is very close to the true output, then this error is 0. And this is L1 and L2 do nothing. These amplifiers do nothing. So you just have a replica of our system. If, due to disturbances and to noise, you have some deviation of the output with respect to the estimated output, then we hope that these terms can do a correction to you. This is a asymptotic observer. Observer or state estimator, okay? And if you optimize in the sense that we will learn later, L1 and L2, then you get the famous Kalman filter. Kalman filter. Have you heard of the Kalman filter? Who has learned about these two words, Kalman filter? No one? Okay, without a Kalman filter, we wouldn't be speaking now, because this is full of Kalman filters, all the system that is used by the computer network to establish the communication or GPS system and so on. Okay, so basically, Kalman filter is an optimized state estimator. Later, we are going to study that. Any question? Now, what we are going to do is to learn systematically how to design this L1 and L2 such that the error goes to 0 according to some poles. Again, we will be able to write some equation for this error, this estimation error E. This satisfies, or if this satisfies some dynamics. Actually, we're not going to use this E, but we are going to use the difference between the true state and the estimate state. Okay, let's call it X tilde. So the difference between the true state and the estimate state, and this will verify an equation. And the issue is, when can I design L1 and L2 such that this error goes to 0? Okay, and of course there is an existence problem, which is for which systems can I design L1 and L2 such that they go to 0? Remember that this is just one example. We are going to do that for the general case for a general state model. And this existence problem will lead us to the concept of observability. Okay? So, like you have when you want to invert a matrix, one thing is to invert the matrix, and the other thing is to know whether the matrix is invertible. So a criteria for the matrix, for a square matrix to be invertible, what is it? The criteria of invertibility.
The determinant being different than 0.
The determinant being different from 0. Okay. Now, we have a similar situation here. We have how to design a controller. And if I do state feedback, I will place the poles where I want. For which class of systems is this possible? So you have the criteria of controllability. One thing is to design the controller. The other thing is to know whether the controller exists, if it is possible to be designed. That's controllability. And also, I want to estimate the system. So one thing is to design the state estimator or the asymptotic observer. These mean exactly the same. And one thing is to design the state estimator, and the other thing is to know whether it is possible to design the state estimator. That is related to the criteria of observability. Okay? So we will start by studying these two criteria that are, say, theoretical concepts similar to invertibility of a matrix. Now we are in the context of control. And later we are going to learn how to design first controllers, state feedback controllers, and then state feedback, and then state observers, state estimators. That's our program. Any question? Okay, so I don't want to erase, I want to stop sharing and go back to the slides. Before we do that, let me show you another example that shows that we should have some structural properties of the state model well established, and these will depend on these concepts of controllability and observability. which are quite magic at the moment, quite obscure. We don't know, just some words. So suppose that you have an unstable process, 1 divided by s minus 1. And I said, well, I'm going to place here a controller, which is very simple. It has a 0 in s minus 1 and a pole in s plus 1. Okay. Now, you might say, but in practice, I will never be able to cancel the pole by 0. But suppose that you exactly cancel the unstable pole in 1. Okay, so this 0 is exactly s minus 1. So the transfer function, there is no doubt, is 1 divided by s plus 1. Now, my question is, suppose that this is a plane, an airplane, and you want to fly to some, say, to Brazil, to have some, Brazil at this moment is not probably the best places, but imagine some idyllic place and you want to fly there, and this is the dynamic of your plane, okay? And use this controller. Use this controller. So my question is, would you enter the plane? That is to say, does it stabilize, really stabilize the plant? When you have this system, how many poles does it has? This system here.
2.
A 1.
Which one? A single one? Which one?
No, both the compensator and the
process. I see 2 actually. One for the compensator, yes, and another for the process. So I have 2 poles. Yes. Yes. So what is the order of the state model? If you have 2 poles, you have 2 state variables. 2, you have 2 state variables. Okay. Now the transfer function, you have a perfect cancellation. So the transfer function just has 1 pole. And the conclusion is that the transfer function is hidden, is hiding something from you. Part of the dynamics is internal. Okay. If you write, you can write, for instance, the state equations in this way. Suppose you have s minus 1, s plus 1. You divide these 2 polynomials and you get 1 plus minus 2 divided by s plus 1. So s minus 1 and s plus 1 has, for instance, this state realization here. Okay. So this block here, minus 2 divided by s plus 1, is the realization of this part. And I call this output state variable x1. And then I have a 1, which is a feed-forward term. That is this line. Okay? And then I have the other term. So if I call this x1 and the output x2, it's a simple exercise that you should do at home. I mean, at least after the class. And you have these 2 equations. Okay? So you have two state equations. The system is of order 2. You can write the matrix A, and you will find as eigenvalues of the matrix A +1 and -1. Okay. So the +1 is there. So you have the positive exponential that else some unstable factor is there. The situation is that it's somewhere inside the system. So if you apply that formula, remember the formula of variation of constants that we studied in the last course, what we have x1 is you have x1 remember is this variable here. X1 is a negative exponential times the initial condition minus a negative exponential convolved with the input. Okay, this convolution is that integral. Okay, is that integral? Suppose that r is 0, this is not even there. Now, what about x2? X2 is the output. Then you have a positive exponential, good Lord. You see, you have a positive exponential times x2 0. And also a positive exponential times x1 0. So associated, so the input is very well behaved. You just convolve the input with an exponential of minus t, which corresponds to the fact that the input output is just 1 divided by s plus 1. So you have a pole which is minus 1. But then the initial conditions are associated to eigenvalues associated with the unstable pole. Okay, so this example shows that you have more information in the state model than in the transfer function. If you start doing pole zero cancellations, actually you are throwing away information. And if this cancellation is done with unstable poles, then you get into trouble because you are forgetting that the input will not excite these unstable poles, at least in this case. But there are initial conditions that can excite those poles. Remember that the transfer function is what? Is the Laplace transform, or is the quotient of the Laplace transform of the output divided by the Laplace transform of the input with 0 initial conditions. So this means what? That the transfer function assumes that x2 0 and x1 0 is 0 and says, well, yt is just the convolution of the input with the exponential of minus t, which is the impulse response of the stable part. Okay? But then when you have non-zero initial conditions, these two terms appear. There is also this story that if you do pole zero cancellations, you reduce the order of the system. So there is an interplay here between the order and what is inside the transfer function. And again, we are going to see that this is related to these concepts of controllability and observability. Okay. So by this time, I hope you would like to know what is controllability or observability. Another possibility is that you are thinking about lunch and say, well, the guy should shut himself. But let me show you something about, let's consider these concepts. Okay, before lunch. Let's start with controllability, and you can have this definition in continuous time and in discrete time. What is the definition for continuous systems? Suppose that you have a linear state realization, x naught equal to ax plus bu. Okay, okay, so this is completely controllable or reachable. Sometimes we just say controllable. Reachable in Portuguese means atingível. If you start with the initial condition at the origin, look at this diagram, then there is a sequence, a control function that drives you to any point in state space in a finite time. So I have my state at 0 at the origin. and I specify a point at XF, and this point can be anywhere, could be here, there, and so on, could be anywhere. The state realization is controllable if, this is a definition, so this is if and only if, I can find a sequence or a control function that in a finite time interval drives me from the origin to the specified final point. So this is the definition. How can I see whether a system is state realization is controllable? So there is a theorem that says that you build this matrix, okay? Don't get confused of this C with a output C matrix. So this is a calligraphic C, but I don't know how to do calligraphic Cs in this word processor. So I wrote this one. So this is the so-called controllability matrix. And how is the controllability matrix made? So you put first column B, second column AB, then A squared B, etc., up to A, up to N minus 1B, where N is the dimension of the state. So this is square because the length of each of these columns is B, and you have here, the length of each of these columns is N. You have N elements in B, N elements in AB, and so on. And you have N, you start A0 and you end A N minus 1, so you have N columns. So this is N by N. Okay? Now, the pair AB will be controllable if the rank of this controllability matrix is equal to the dimension of the state. Okay, so this state realization is completely controllable if and only if the matrix, this matrix, has rank equal to the dimension of the state. Any question?
That capital B is the small b?
Oh, yes, that's right. This should be a small b.
Okay.
Thank you. More questions? Don't get confused. Don't get confused with this is the definition, and this is a theorem that has to be proved. Okay, we are not going to prove this theorem for the continuous time case, but we shall do it for the discrete time. If you want to see the proof, in my book you have a concise proof of this in continuous time as well. But here we are just going to see the proof of this criterion for discrete time. Okay, so yes,
teacher.
yes. Mm-hmm.
In this case, can we not only say that the matrix is totally controllable if it has dimension x, and if it doesn't have dimension x, we can only say that it's not controllable? Or can we measure like it's more controllable than?
Yes, if you look at the rank of C, suppose that your state is 2, as I mentioned 2, and the rank is the rank of the controllability matrix is just 1, then this means that you will be able to attain states along a line. So the rank of the controllability matrix tells you the dimension of a subspace that you can attain, which is not necessarily aligned with the axis for x1 and x2 and so on. I will show you one example in a moment.
Okay, understood. Thank you.
So in this case, what we have, this is clearly not completely controllable. You understand why? Look at the block diagram. Do you mind while you think that I open the door to the postman? just a moment. Think why this is not completely controllable. So, any thoughts? Think of the definition. Think of the definition. By starting from 0, 0, you should be able to attain any point in space, state space, by manipulating the input. So suppose that I want to go to a state which is 2, 2, x1 equal to 2, x2 equal to 2. Can I do it?
You can control x2 with the input, right?
Yes, we cannot affect x2. So x2 does not change. So this is not controllable or completely controllable. Okay, but actually it is possible to show that you can attain any value for x1 in this simple case. Okay, so the possible set of values for x1 that you can attain is just the x1 axis. So if you want to go to 2, 2, it's impossible because you can't take away x2 from the origin. Okay, this is, you can say, but I don't need too much mathematics to understand that. The problem is that in many cases, you won't see the diagram, okay? Even in a 2x2 system, I could do a change of variables and rotate this, and the answer would not be obvious. Now, imagine that you have an electronic circuit, an integrated circuit, say the chip that you have in your processor, microprocessor in your computer, and this has a state of, I don't know, 500,000 variables. If you think of it as an electrical circuit, and this is not merely a curiosity. The guys who do simulation to validate circuits in microelectronics must do some sometimes controllability checks. Okay, and we have 500,000 states. So which ones are controllable? Where can I go? Which tensions, distributions of tensions can I have, and so on. Okay, let's go ahead and okay, write the state equations in this way. So I'm not going to do it here, but you should be able to write these equations from the block diagram. And now build. Now the dimension of the state is 2, so the controllability matrix is B and AB. So B is 1, 0, 1, 0, and AB is just multiply A by B, and you get minus 2, 0. And clearly the rank of this, you have all these two vectors have just one dimension. So the rank here is just one. I used here the Portuguese symbol car because in rank in Portuguese is característica, but I should have used rank in English. Okay, so this was, let me show you another example before we end the class. Suppose now that we have two circuits or two systems that are similar, okay, are similar, and now x1 and x2 swing together. They swing together. Okay, they are always proportional. So by manipulating U, you can only reach states that are such that x1 is equal to x2. If I want to go, for instance, to x2 equal to 5 and x1 equal to 0, so a point here, it would be impossible. Okay. Now let's see what happens. Yes, yes.
What changes should we do to the system to make it controllable?
It depends on the system.
But in this specific one, is there like anything we could do?
The controllability depends on the placement of your actuators. So you mean in practice? I mean, I come to the conclusion that my system is not controllable. For instance, if you have, imagine that you want to heat your living room, and you put a heater in the corridor. Okay, so the system is not controllable. You should change the position of your actuator, in this case of your heater. Okay, now this is an anecdotal system, but suppose that you have a boat. Now we have this story of this large boat that carries containers that is blocking the Suez Canal, and it has a lot of propellers. And you should place the propeller such that you are able to make the system controllable. That is to say, you should reach within at least some range all possible specified positions and velocities. And this is a very large container ship. Okay? I remember once a colleague from yours, he was a student of naval engineering, and he approached me with a problem from a boat, and the problem was how to place the propellers in the boat such that the maneuvers, he could do all the possible maneuvers. And also you can think, I want to do it with the least possible energy. That is still another problem. But in a word, to answer your question, controllability is related to the position of your actuators. If your actuators are not in the correct position, then the system will not be controllable. Okay? Sometimes we have a problem because you have a system designed by a mechanical engineer or by a chemical engineer, and then you are the control engineer that comes and the way the system has been built is not the best option for control. I remember once that I was approached by a colleague from the chemical engineering department. He had the problem of keeping the temperature constant in a chemical reactor. And what he was doing, he was putting all sorts of thermal insulators. Okay, so basically it was causing the system to be non-controllable because the heater was outside the insulators. Okay, so you were heating, but the heat was not coming into the reactor. Instead of creating the system of making the system very well insulated, that he was never able to do it, you should remove the insulation so that the actuator, that is to say the heater, is in contact with the reactor. So if your system is not controllable, you should be careful. First, check whether the actuators are where they should be. And second, in some cases, you have modes that you can't control, but these modes are naturally stable. Okay, so in that case, maybe this is not a problem. Your system, because in some of the modes, some of the states, you can drive to zero, you can stabilize by your controller, and there are some other modes, some other states that you cannot control, but they are naturally stable. Okay, and in that case, you cannot improve them, but at least they do not affect the stability of the system. Let me just conclude this this example. So we have in this case, two systems that are in parallel with the same a function, okay, with the same coefficient, and if I compute, in this case again, n equal to 2, so I have B, I have AB, and the column number 1 is proportional to the column number 2. You multiply by -1, so the rank here is 1, so the system is not completely controllable. Okay, actually, these two examples, you see, in one example you are not affecting the part of the system which is not controllable. In the other example, you have states that are proportional one to the other. These are mechanisms that appear, and we are later going to take conclusions in a more general setting about this type of systems, of mechanisms. So today, to end up, we ended, there was this long motivation, and then we introduced this concept of controllability, which, as you are going to see later, it's very important, it's instrumental for controller design. A final question? Okay, if not, remember that next week we won't have lectures, and there are Easter holidays. We are going to have Easter holidays, and we will resume in the week afterwards. So have good and refreshing holidays and a good weekend. Bye-bye.
Okay, thank you.
Bye. Thank you.
Thank you.
Thank you. Bye-bye.
Bye.